Hi, I'm Luciano, and today I want to present the work that I did in collaboration with Politecnico di Bari, Università di Messina, and Chinese Academy of Sciences. It is named spin torque diodes for computing multiplication, and in fact, today I'm presenting an innovative way of using spin torque diodes for the computation of the multiplication and convolution operations and the application of those in neural networks. But first, what are neural networks? Those are human-inspired softwares that are entering in every field of technology and also in our daily life. We can see here on the right an example of an autonomous driving vehicle that an image from those vehicles that need to understand at every moment what's happening in their surroundings. And because of these real-time applications, there is a need for higher performances devices. And so the semiconductor manufacturers are focusing their attention on neuromorphic and unconventional solutions, like the one I'm proposing today, for the implementation of neural networks. And we know that the convolution is the most expensive operation, and in order to make that more time and energy efficient, we can use hardware solutions. And today we have two main hardware solutions. In the spintronic field we have the use of memristors, and in the optic field we have the use of phase change materials. So what is the convolution? The convolution is an operation analogous to the dot product, but it concerns images and filters. We can see here from the definition that it is an accumulation of multiplications, and the critical part are the multiplications. For this reason, we find a way to implement the multiplication using any parabolic phenomenon. So given an ideal parabolic phenomenon P of x, and given two numbers that we want to multiply, f and g, it's easy to derive the mathematical formula f times g, starting from three measures of the parabolic phenomenon, P of f times g, P of f, and P of minus g, with a very quick mathematical conditioning. And to use this technique, we need a parabolic phenomenon. For this reason, we observe the degree of match. And given two coupled oscillators, the degree of match is defined as a sort of an average between the oscillatory components, in which each oscillatory component has a module part, a phase part, and a frequency part. But in this case, we are observing frequency-locked oscillators, so the frequency part can be neglected. In particular, we can see from the work of Chiarulli that realized the degree of match with CMOS oscillators, and from the work of Yogendra that simulated spintronic oscillators, we can see that if the oscillators are frequency locked, the DOM has a parabolic trend. And we wanted to reproduce this degree of match with Slavin's model, which is a model suitable for the reproduction of spintronic oscillators. But I won't go too much into detail about this, since we just published an article on solid-state electronics. So if you want more info about this, you can check out this one. But the main message that I want to communicate here is that we observe that the DOM has a clear regular behavior when the two oscillators are frequency locked. And if we focus our attention on the peak of this regular behavior, we can see that it has a clear parabolic trend. And since it has a parabolic trend, as we said a couple of slides ago, we can use that to implement the multiplication. And here it is shown an example of 10,000 randomic multiplications represented by the blue dots that are compared with the ideal result represented by the orange line. But there is one main problem with this technique, that to implement the DOM we need the amplitude and the phase components of the two oscillators, and those are very hard to measure on chip. So we wanted to find a physical analogy to the degree of match, and we defined the degree of rectification. We observed the work done by the experimental work done by Fang and others in 2016, and it is represented the rectification curve, so the VDC versus IDC curve, and it has parabolic behavior near the peak. Moreover, we are observing continuous currents and continuous voltages, and those are very easy to input and to measure. To work properly, the diode must be injection locked with an external signal, an external current signal. So, comparing to the previous case, previously we needed two oscillators that are frequency locked, and here instead we only need one spintronic oscillator, one spintronic diode that is injection locked with an external current signal. We can see from a time trace that the transient time in this case is about 10 nanoseconds, and this can give us an insight about the speed of the implementation of the multiplication with this technology. And in this case, no applied magnetic field is needed. So we wanted to reproduce these results also with micromagnetic analysis, and we can see that the continuous voltage can be defined and can depend mainly on two variables that are the power of the magnetoresistive signal and the intrinsic phase shift between the external signal and the magnetoresistive one. And from a time trace, as you can see here on the right, where the external signal is represented in red and the magnetoresistive signal is represented in blue. From this plot we can have an insight about what is the intrinsic phase shift between the two curves and what is the power, since it scales with the amplitude of the magnetoresistive component. And in order to have a parabolic phenomenon, and in particular the peak of the parabola, we have this phase shift to be close to 0, to pi, or multiples of pi. And for this reason we made a systematic study with different frequency configuration, so different frequencies of the external signal and different input continuous current applied. And we obtain that the phi gets close to 0 when we approach, so in this blue line that is very close to the injection locking limit. In particular, we focused our attention on the case where the external frequency is about 800 megahertz, and we can see here in the plot in the middle that in green it is represented the intrinsic phase shift, and we can notice a quasi-linear behavior, and also in blue it is represented the amplitude of the magnetization. But if we take a look of the y-axis of this amplitude of the magnetization, and we want to make a coarse analysis, we can pretty much consider this one constant. So we can use those data to obtain the continuous voltage that we have in output. And we can see from this plot there where the simulation values are obtained in blue, we can see that those have a clear parabolic trend, also compared to the ideal parabola represented by the red line. And moreover, we were able to estimate the parameters of this parabola analytically, and the analytical one is represented by the red dots here, the red dotted line. And for the symmetry of the parabola, we need only half of the curve. Half of the curve is sufficient to compute the multiplication. And getting back to the experimental curve represented by Fang and others, if we extract the data from the peak here, we can see that also these data have a parabolic trend, and so we can use those parabolic trends to obtain the convolution. In particular, we use an example, an exemplary image of a snake convolved by a blurring filter. And here you can see the result of ideal convolution, the simulation-based Dor convolution, so the one using the curve from the previous slide, and the experiment-based Dor convolution using the curve from this slide, so the curve here on the top. And what is interesting is that repeating this process for 1,000 randomic filters, we observe that the correlation between the observed convolution and the ideal one is above 96% for the experiment-based Dor, and it is above 99% for the simulation case that we can consider as a theoretical benchmark. In conclusion, we applied the Dor-based convolution also to solve the MNIST recognition problem, so to recognize handwritten digits. And we did so implementing a very small neural network that in the starting case gave us the accuracy of 98.6% of success recognition. And we applied the Dor technology to the convolution layer here, and we obtained a drop of about 2 point percentage in the accuracy. So we obtained 96.8%. But then after a very quick update of the weights of the fully connected layer, we obtain an accuracy of 98.4%. So we restored the starting accuracy. And this is a clear sign that the analysis that we are doing, that the technology that we are proposing are applicable for neural networks applications. And in conclusion, we can say that the degree of rectification is a fast, easy to measure and applicable technology for the implementation of the convolution, and its applicability in neural networks has been supported by the degree of match theory, micromagnetic analysis, and an exemplary application. We submitted a paper at the Physical Review Applied, and hopefully it will be published soon. Thank you for your attention.